Okay, so we're working on antiderivatives part 2. So let's just recall what we did last time and maybe do one example. So last time we essentially learned the antiderivative rules for polynomials. So antiderivatives of polynomials along with the notations. So basically the three rules, we'll just break it down to two because the antiderivative of 0 really doesn't come up often. So if you're finding the antiderivative of some constant k, say dx, then this would have antiderivative kx plus a general constant c. If you were finding the antiderivative, here's the big one, of say x to the n dx, this would be x to the n plus 1 divided by n plus 1 plus some constant. So let's just compute an example. So I don't know, the antiderivative of 15x squared minus 11x plus pi, let's say. Well, we just remember we also learned that you can do the integrals term by term. So we just do them one at a time utilizing the two rules. So basically we just add 1 to the power of x and then divide. So it'll be 15x cubed over 3 minus 11x squared over 2. And pi is just a constant, right? So we would just stick an x on next to it as stated in rule number 1. And, we can do maybe one simplification. This is 5. 15 over 3 is 5. So we have 5x cubed. I mean, you could call this 5.5 if you wanted, but I'm just going to leave it as 11 over 2. And that would be our answer. So that's it really for that example. So that pretty much single-handedly allowed us to find the antiderivative of any polynomial. So let's look at exponential and logarithmic. So we'll start with exponential. So since we saw that essentially antiderivatives were reversing the process that the derivatives were doing, we're going to try and first remember what the rules we had for finding derivatives of exponential functions were. So our goal here is to find antiderivative rules for the exponential functions. Excuse me. So there's two forms that we would typically write them in, either continuous form or standard form. So continuous form, in its most general sense, would look like something like y equals e to the kx. And the other form, we might just have something like y equals a to the x. So let's remember what the derivative rules did. So the derivative rules, because what we want to do is do this process in reverse, essentially. So if you were taking the derivative of e raised to the kx, what happens? Well, you just bring that constant down k and multiply it with e to the kx, right? This should be familiar. Remember, the derivative of e to the x is just a self e to the x. So if you had the derivative of, say, e to the 5x, that would be 5 times e to the 5x when you do the derivative. And the other form would be a to the x. And when you take the derivative there, it's natural log of a times a to the x. So really the process of doing the derivative isn't that hard. We just, so our procedure is take the same function for number one and multiply by k. And this one is just take the same function and multiply by the natural log of a. So if you were trying to reverse the process, what we do is we just do the inverse operator. So we're not going to be multiplying, instead we're going to be dividing. So to find antiderivatives, we should simply be dividing by the appropriate constants. Now, that's not a mathematical proof. It's just essentially a mathematical guess. But what we can do is we can go ahead and check with all the examples. Remember, if you ever want to test that something is actually an antiderivative, you just take the derivative and make sure it returns the function in question, the function you're starting with. So let's try and put this process to work and see if it in fact does work. So example. What is the well, let's use the same notation because we're already used to the notation. So I'm just going to say compute each indefinite integral. So maybe we're trying to integrate, say, e to the 3x dx. Now, this was the first derivative rule we looked at. So the derivative of e to the 3x would be 3 times e to the 3x. So our guess for the antiderivative is rather than multiply by 3, we should be dividing by 3. So our guess for the antiderivative would be 1/3 e to the 3x and then plus a constant. And we can check that by taking its derivative. If you take the derivative of 1/3 e to the 3x plus a constant, so we take the derivative. Well, we know the derivative of the constant is always 0, so that goes away. The derivative of the first part would be 1/3, and then we use the derivative rule for e to the 3x, which is 3 times e to the 3x, which just leaves us with e to the 3x, which was the original function we were trying to integrate. So the check does work. So it looks like that rule is effective for the first form of the exponential function, the continuous form. Now let's look at an example with the standard form where the base is not e. So let's try and integrate maybe 7 raised to the x power. So from the derivative rules, you'll recall the derivative would be the natural log of that base, 7, times the same function, 7 to the x. So our guess, again, is that we're just going to divide by that constant rather than multiply by it. So we think it should be 1 divided by the natural log of 7 times 7 to the x plus a constant. And again, we can check that by taking the derivative, and you'll see what happens when we take the derivative is that we'll get the right cancellation, right? Taking the derivative, we have 1 over the natural log of 7 times the natural log of 7 times 7 to the x, and then that constant vanishes. So These go out and everything checks out. We're left with 7 to the x, which is exactly what we're starting with. So are there any questions so far? Check the chat here. Nope, no questions. All right, let's go back to OneNote then. So let's write down what these general rules look like. So the antiderivative rules. For exponential functions. So first, we have the standard form, the integral of e to the kx dx. So we're saying this is just going to be 1 over k times e to the kx plus c. And the second form, the integral of, say, a to the x dx would be 1 over the natural log of a times a to the x plus c. So those are our two rules. And again, one of the reasons that they talk about e being one of the most important numbers of calculus, right? If pi is the most important number of geometry, usually e is thought of as the most important constant in calculus. E to the x, right? It's unique in the sense that e to the x is both its own derivative and both its own antiderivative. So that's not really true with any other function. So yeah, that makes it pretty special. I've got a joke I could tell about it, but I don't know if it would go over well on WebEx. You know, I like to hear the collective groans of the class usually when I tell them. So we'll just try to do some actual concrete examples. So let me do 2 more of these things. Oh, did I not? Well, let's talk about the logarithm first. So the logarithmic function is well, we won't know the antiderivative of the logarithm, but there's a special case for one rational function. So so here's a question. What was the derivative of, let's say, y equals the natural log of x? Okay, so just as a reminder, when you take the derivative of the natural log of x, this comes out to 1 over x. So that means if you reverse the process, it means that in some sense it's telling us an antiderivative, right? If you know the derivative of something, you also know the antiderivative of something. So that would tell us that this one, so we can guess. So let's say this. If we reverse the process here, because right, if you think about taking the derivative of the natural log of x, you get 1 over x. So if you would go the opposite direction, that should be the antiderivative, right? So this is the derivative, and this is the antiderivative. All right, that's kind of as a diagram. So if we reverse the process, we find the antiderivative of 1 over x. With one small adjustment, let's say. And the problem lies in the domain, right? So we know the domain of the natural log of x is just positive values. The only thing you can plug in into the natural log are positive values. It can, its range is all real numbers, but its domain is only the positive x values. So if you're taking the derivative, that's fine. That's not going to affect anything because your inputs have to be legal for that to make sense. But the problem is if you start with 1 over x, 1 over x has a domain of every number except 0. You can plug negatives into 1 over x, and when you plug a negative into 1 over x, that value is itself negative. So when you try and plug that back into the natural log, you would end up with a domain error. So if you're trying to take the antiderivative of 1 over x, it doesn't make sense to have something that's negative there. So for this reason, the antiderivative is actually the natural log of the absolute value of x to make sure that that input remains positive. So keep that in mind. So what happens here is, so the antiderivative of 1 over x, so this is another rule. So the antiderivative of 1 over x dx is the natural log of the absolute value of x plus a constant. So another thing to note is, note that the power rule for polynomials and power functions does not work here. Right? What am I talking about? Well, you could think of the integral of 1 over x dx as the integral of x to the negative first power dx. And we said, well, if you have x to a power x to the n, you just add 1 to the power and then divide by that number. So if you try to use the power rule, you end up with x to the negative 1 plus 1, which is 0. And then you have to divide by negative 1 plus 0. So you end up with, negative 1 plus 1. Which is undefined. So for this one special exception, 1 over x, we have this different rule. We know that its antiderivative is actually the natural log of x. So, yeah. So let's go ahead and do a couple practice examples with the exponential rules and also this 1 over x rule. So I'll just say compute. So whenever you're doing these antiderivatives, it's always important to look at the term and say, okay, what kind of function is this in order to know which kind of rule to apply. So let's say we do the integral of e to the 0.4x plus 7x dx. So you do each term separately. So again, this is exponential and this is polynomial. So we're using two different rules here. We're using the rule from last time on 7x, and we're using one of these new rules for the e to the 0.4x. So the first one, we have 1 over 0.4 times e to the 0.4x. And then for 7x, this is where we add 1 to the power and then divide by that number. And then we just add a general constant for both of them. So 1 over 0.4 can actually be simplified to either 5 over 2 or 2.5. So I'm going to write it as a fraction, 5 over 2 e to the 0.4x plus 7 over 2 x squared plus a constant. Let's do another example. or utilize the other rules we've seen. Let's say we have the integral of 1.8 to the x minus 11 over x dx. So again, this is another example, the first term of something that's exponential. It's exponential where we're going to have to use rule 2 because the base is an e. And the other one, this is really 11 times 1 over x. So we're going to use the 1 over x rule there. So what do we get? Well, remember this one is the same function, but divided by the natural log of the base, 1.8. And the second one, we just leave the 11 in front, and then we know the antiderivative of 1 over x is the natural log of the absolute value of x plus c. So that's how we're making use of these rules. It's always important to keep in mind. Polynomials seem to be the most common examples we have in the book, and kind of they're the most straightforward and probably the functions you're most familiar. But that doesn't mean to take the antiderivative of anything. You can just add 1 and then divide by that thing. I see that all the time, like for part A, e to the 0.4x, I'll see students write like 1 over 1.4 e to the 1.4x, but that doesn't make any sense because you can't just add 1 to that coefficient. It's not a polynomial function. So let me check and see if there's any questions. Any questions? Okay, so let's talk about the fundamental theorem of calculus. Really, there's two parts to the fundamental theorem of calculus, but we're only going to be focusing on part 2 of the fundamental theorem of calculus, which is the connection between these antiderivatives that we've been thinking about and the areas below curves that we were estimating in the previous section 5.1. So it turns out that we can use these antiderivatives to exactly compute the area below curve. So if you exactly know the antiderivative, you're able to find some exact areas rather than just approximations. So the fundamental theorem of calculus, technically this is part 2. So we start with a hypothesis. We have a function that is continuous. So if, let's say, capital F of x is any antiderivative of little f, the net area between f of x and the x-axis from x equals a to x equals b is, so we're going to use the same integral symbol. Now we're going to have some actual limits. The a and b are going to act as limits. So we have an a on the bottom, a b on top, f of x dx. So this is what we're able to compute now. This is known as a definite integral when you have limits. And the way that you do it is you use that antiderivative and plug in the top value and then the bottom value and subtract them. And because you can choose any antiderivative whenever you're computing a definite integral, you're never going to have to worry about that constant of integration. So again, we might want to think about what does the picture look like here. So the picture basically says, okay, you have some curve. You guys have some A value, some B value. So you have some curve. So basically the shaded area is computed as above. Okay, it's a little, it's not as difficult as you might think. So let's start with a very, very basic example. Oh, sorry, didn't mean to go so far down. So let's recall, I'm just going to recall one of the numbers we did. So I'm using Riemann sums, and you can go back and check this because you know how to do the Riemann sum computations. We estimated the area below y equals x squared from x equals 1 to x equals 3 was 8.72. So that's what we got using the Riemann sum approximation. So what we want to do is we want to use this fundamental theorem of calculus to find the exact value of the area. So use the fundamental theorem to find the exact value. So basically what is this? This would be the integral from 1 to 3 of x squared dx. So usually the way you write this is you write down an antiderivative. Again, it's a definite integral because it has the 1 and the 3, and you don't have to worry about any constant when it's a definite integral. So this is a polynomial. It's just x to the third over 3, and we want to plug in 3 and then 1 and subtract them. So if I do that, I would have 3 to the third power over 3 minus 1 to the third power over 3. So this is 9 minus 1/3, which is 26 over 3, or 8.6 repeating. So our estimate was close from the Riemann sums, but it wasn't perfect. All right, so let me also show you a numerical tool. Sometimes this will be helpful if you are stuck and you think you're doing something wrong, but you just want to be sure you have the correct numerical answer. Again, Desmos is really good for this. DESMOS.com. If you go to the graphing calculator, you can check something like this very easily. So if you type in int, it'll give you an integral, and you can just plug in exactly what we had, 1 to 3 x squared dx, and it'll give you that answer. Again, it's got a limited float, so it rounds after, I don't know, 10 decimal places or something. So it gives us 7 at the end, even though we know 6s repeat forever, but it's basically agreeing with the answer that we found. So it lets us know we didn't make any mistakes there. So any questions on that? So yeah, usually since you're learning from home and you're always going to have your computer available, you don't really need to have a fancy calculator. That Desmos site works great. You can also use a calculator if you have one and you're comfortable with it, or if you have another website you like to use. There are plenty of them out there. I've just been using Desmos for a few years. Graphing is pretty easy. Okay, so let me do a couple more. Well, how much time do we have? Why don't I give you some problems to work on, and we'll see how they go. I don't know. I have a whole bunch. But let's see if we're at least getting the concept. So let's try. So, for example, so I just say compute. So let's say I'll just write the problems here so they'll all stay on the board easily. So we'll go 0 to 4 of 6x minus 5 dx. On Desmos, you have to be careful too. Some syntax places will require like a parentheses here to highlight the argument. I usually don't. I'm a little bit lazier when it comes to parentheses there. I don't think they're necessary, but I mean, it's just notation, so it kind of depends on who's writing it. So the second one, integral from 1 to 3 of 1 plus 2x minus 4x cubed dx. C, let's say the integral of 4 square root x from 1 to 9. Again, remember, square root of x is the same thing as x to the 1/2 power. Let's say d, we have the integral from 0 to 2.6 of 8.4 e to the 0.4 t dt. Right, we don't have to use the letter x. Sometimes we'll use t. E, let's say the integral from 1 to 2 of 1 over x plus 3x squared dx. It's kind of ugly too. Let me make it a little bit better. Okay, so I'll split you up into 5 groups to work on these. Again, it's going to give you practice using the rules we see, in exponential. The first 3 can all be done with polynomial. And then we have the 1 over x rule coming in part E. And then we have to plug in the numbers. So it's pretty straightforward. Okay, so let me break it out into groups. Again, however they shake out. Group 1 will do A, Group 2 will do B, Group 3 will do C, Group 4 will do D, and Group 5 will do E. So let's try the old breakout sessions.
Professor?
Yes.
So since we don't know what group we're in until it's gone, are we supposed to just write all of them down?
Well, I'm going to switch back to the screen so you can see the problems.
Oh, okay.
And then leave it up on that screen, if that makes sense.
Yeah, okay, because last time when we switched to groups, we couldn't see the problem anymore.
Oh, so yeah, that's when I had to like leave and then come back. I wonder if I try to, if I can do like half and half, if it'll fit. Maybe I can make it smaller. Is that possible? Zoom out a thing. Let me just try and extend it a little more. It's nothing's ever easy. Okay, let's see if this works. Okay, so can you guys still see everything?
Yes.
Okay, so I'm going to start the breakout sessions here. So if they don't work, please let me know, and I'll try to leave and come back. So maybe that's the problem. Can you guys still see stuff or no? So I'm not sure what went wrong there. It looks like... I don't know. Real quick, I'm just going to leave and come back and see if that fixes everything. Hi, everyone. Sorry, I don't know what happened with the breakout sessions, but I guess it didn't work. So I'm just going to share my screen, and then we'll go through these. So hopefully you're able to make a little bit of progress. I'm not sure if there's a better way to do it in the future. I'll check into it, though. Okay, so let me share this again. It seems like stuff stops working whenever we do these breakout sessions. Okay. So for part A, let's go ahead and go through that one. So for A, it was the integral from 0 to 4 of 6x minus 5 dx. So what we do is we do the antiderivative, which is going to be, 6x squared over 2 minus 5x. That's the antiderivative. And we need to plug in 0 and 4. Before I plug in, I'm going to do 6 divided by 2 and say that's okay, 3x squared. Polynomials are usually nice when you have 0 to plug in, because when you plug in 0, everything kind of goes away. So there's two parts here. We plug in the 4, so we get 3 times 4 squared minus 5 times 4. And then you would also subtract plugging in 0. So you would actually need parentheses here, because if you have more than one term, that negative would distribute. So you get 3 times 0 squared minus 5 times 0. There's not too much of an issue here, though, because everything in the second set of parentheses becomes 0. So this should just simplify to 28. So was anyone that worked on this problem able to get 28?
That was our problem, but we didn't get that, but I see how you got it now.
Any insight as to where things might have gone wrong? Was it, did you plug in like a 4 and then a 0? Because I could see that happening.
Yeah, so we were close. We just didn't. I think that's probably what went wrong.
Yeah, you might see somebody do like 3 times 4 squared minus 5 times 0, but you have to plug in the top number into every single x, and then subtract, and then plug the bottom number into every single x. So
Okay.
that might have been a place where perhaps you had a mistake. Okay, so let's move down to B. B is going to be pretty similar as well. It's also a polynomial. So it's the integral from 1 to 3 of 1 plus 2x minus 4x cubed dx. Again, you just have to do lots of these problems because there's lots of places you can make mistakes, and it's all very new to you still. And you spent all of last semester thinking about derivatives. Now you're doing all that stuff backwards in your head. So it's really, anytime you look at a function, try and think, okay, well, what would the derivative be? What would be the antiderivative? You want to look at a handful of examples. Okay, so here, antiderivative of 1 would just be x. The second one would be 2x squared divided by 2. So we know the 2's are going to cancel. So I'll do it for now, but 2 over 2 is going to end up as 1. And then 4x to the 4th over 4. So these simplify quite nicely, and we're going from 1 to 3. So this is really just x plus x squared minus x to the 4th from 1 to 3. So now I'm going to be plugging 3 in 3 different places, and then I'm going to be plugging 1 in 3 different places and then subtracting. So basically I've got 3 plus 3 squared minus 3 to the 4th minus 1 plus 1 squared minus 1 to the 4th. So you can use your calculator for this part, and you would just end up with minus 69 minus 1, which is minus 70. And so what would that mean for this picture? Well, likely the majority of the area is going to be below the x-axis if you were going to graph this function and then look at that function from 1 to 3. So remember, the integral is giving us the signed area, so areas below the x-axis are going to read as negative. So was group 2 anywhere close on that problem?
Yeah, I got that answer.
Okay, great to hear. Okay, so then the last 3 were some of the newer rules, so they might not have been as straightforward to you. So the integral I have from 1 to 9 of 4 square root x dx. So again, the helpful thing is I mentioned to write this as x to the 1/2. So when you write this to the 1/2, we're using the polynomial and power function rule. So we're just going to add 1 to 1/2 and then divide by that number. So when you add 1 to the exponent, 1/2 plus 1 is going to be 3 over 2. So this will be 4x to the 3 over 2 divided by 3 over 2. And remember, whenever you're dividing by a fraction, it's exactly the same thing as multiplying by its reciprocal. So instead of writing divided by 3 over 2, I'm just going to multiply by 2/3. That means exactly the same thing, right? 1 over 3 over 2 is exactly equal to 2 over 3. So that's all I'm doing there. So I get 4 times 2/3 times x to the 3 over 2 from 1 to 9. And that's 8/3 x to the 3 over 2 from 1 to 9. Okay, so I've simplified stuff with algebra enough, so now I'm just going to plug in the numbers. So I get 8/3 times 9 to the 3 over 2 minus 8/3 times 1 to the 3 over 2. And this comes out to either 208 over 3 or 69.3 repeating. So there, rewriting stuff using algebra makes the problem a little bit easier. So I think what I'm going to do is I'm going to save a little bit of time for questions. We'll start back with D and E next time. So if you were working on those other 2, but let's see, if you're working on them and you wanted to know what the answers are, I'll write down the answers for now. So the answer to D was approximately 38.41. And the answer to E was approximately 7.69. So if you were assigned one of those problems and didn't have time to finish, but you still want to work at it, you can go ahead and see if you can confirm those results. Also, you can check maybe on Desmos that you can type it in and see if what you type in on Desmos agrees with that result there as well, so that you know that you can numerically evaluate these expressions using that calculator. So, okay. So are there any questions for me? Also, I don't know if you saw yesterday, I got all the other recordings posted and the notes from those WebEx meetings as well. So I'll be doing that from now on. in addition to the old lectures that are already up.
I had a question.
Yeah, go ahead.
You think we'll be able to go over some of the homework on Monday?
Probably it's gonna be all the way on Friday, so the day it's due. That's probably the day. If you have a question or two, we can look at that from this section. But maybe one or two questions on maybe Monday or Wednesday, and then we'll spend Friday going over all the ones that you weren't able to finish.
Oh, okay.
Because we'll probably have a little bit of time for, let's say, 5.2 questions. I want everyone to get a good amount of practice with this stuff. Because again, it's the opposite direction of derivatives. So it's it's like driving your car backwards. If you don't do it that often, you're not as good at it. So we kind of have to get used to both directions.
Okay.
But yeah, we'll have some time for questions. But next Friday, I'm going to dedicate just to the homework. So anything we don't get to Monday or Wednesday, we'll take care of on Friday.
Okay, cool.
Anyone else? Okay, well then we will call it a day here then.
All right, thank you.
Thanks.